In this video, we're going to talk about finding the zeros of a polynomial function and their multiplicity. All of these things are building to actually creating the graph of a polynomial function. We just learned how the graph of a polynomial function behaves on its ends based on the degree and leading coefficient. So now we'll figure out what happens in the middle. And so key points in the graph of any function f are the x and y-intercepts. We found x-intercepts multiple times throughout the course, but recall that x-intercepts are ordered pairs R0 such that R is a real number solution of the equation f of x equals 0. Right? To find the x-intercept, we set y equal to 0 and solve for x. The solutions are also called the roots or zeros of the function. The zeros of a function are the values that make the function 0. So there's some properties about the zeros of a polynomial function. If f is a polynomial function of degree n and r is a zero of f, then the following statements are satisfied. There are n zeros of the function, including repetitions. The zeros can be real or complex. The value r is a solution of the equation f of x equals 0. That means that f of r is equal to 0. If r is a real number, then the ordered pair r0 is an x-intercept of the graph of f, and the expression x minus r is a factor of the polynomial f. So I want to look at a polynomial in this example and find the zeros. F of x equals negative x cubed plus 6x squared minus 9x. To find the zeros just means find the values of the x-intercepts. So we would set this function negative x cubed plus 6x squared minus 9x equal to 0. And we could do that by factoring. Notice that there is a common factor of an x, but we take out a negative x since the first term is negative. When we factor out a negative x, we get an x squared minus 6x plus 9, and that's equal to 0. And then we can factor x squared minus 6x plus 9 as x minus 3 times x minus 3. And notice this is really the same thing as negative x times x minus 3 squared is equal to 0. So when we set these factors equal to 0, we get negative x equals to 0, or x minus 3 squared equals 0, but that is equivalent to just x minus 3 equals 0. Dividing by negative 1, we get x to be 0, or adding 3, we get x equals 3. So in the previous screen, I just said that if the degree is n, we should have n zeros. Well, that does include repetition, so because of this square, we say that there's actually a multiplicity of 2 because the 3 repeats twice. And then the 0 of 0 has multiplicity 1 because it occurs just one time. Now, I have on the screen actually the graph of this because we're going to make some conclusions in just a minute about the zeros and how many times they repeat and how the graph behaves at the zeros. Some other things I want us to start putting together is that the degree of this is 3, which is odd. So that tells us it will do opposite things at its end. The leading coefficient is negative 1, which is negative. So that tells us it's going to go down to the right. Therefore, it will go up to the left because odd does opposite things. And we can see that here. This graph starts in the second quadrant. It goes through 0, 0, which was one of those x-intercepts we just found. It goes to a point, looks like almost like 1, negative 4, and then it comes up to this point of 3, 0, and then it goes back down. So notice how the graph behaved at these zeros. At 0, 0, the graph crossed the axis there, but at 3, 0, it touched or bounced off the axis, and that has to do with the multiplicity, or that is the number of times that the 0 actually repeats itself. Because the 0 of 0 occurred only one time, right? This negative x to the 1. It crossed the axis at 0, 0. But the 3 had this power of 2 on that factor x minus 3, so that means it's going to bounce off at 3, 0. So it's really like the graph is behaving almost like y equals x at this 0, 0, and y equals x squared at this 3, 0. So we can summarize this. We say that if r is a 0 of a polynomial function f, then r has multiplicity k if x minus r to the k is a factor of f. That is, a value r is a solution that repeats exactly k times. The multiplicity of a 0 r determines how the graph behaves at that 0. If the multiplicity is odd, then the graph will cross the x-axis at r0. If the multiplicity is even, then the graph will bounce off or touch the x-axis at r0. And these facts will all help us graph a polynomial function. They'll also help us solve polynomial inequalities, which we'll get to in a couple of sections. So in this example, we want to describe how the graph behaves at the zeros after we determine those zeros and state their multiplicity. We have the function p of x equals 0.2 times x plus 2 times the quantity 2x minus 3 all squared. So to find the zeros, we set that function 0.2 times x plus 2 times 2x minus 3 all squared equal to 0. Well, since this is factored, we can just set each factor equal to 0 to solve. 0.2 doesn't have a variable in it, so we don't need to worry about that. We can set x plus 2 equal to 0, or 2x minus 3 quantity squared equal to 0. So we get x is equal to negative 2. If 2x minus 3 squared equals 0, then 2x minus 3 equals really plus or minus the square root of 0, but that's just 0. So 2x is equal to 3, and x is equal to 3/2. We have a 0 of negative 2, which has a multiplicity of 1 since x plus 2 to the 1. And then we have a 0 of 3/2, which has a multiplicity of 2 since 2x minus 3 quantity squared was a factor. So how would the graph behave at these zeros? Well, because the multiplicity is odd for negative 2, then the graph will cross at 2, 0. And because we have a multiplicity that's even for 3/2, the graph will bounce off or touch at 3/2, 0. And I have the graph drawn for you so that you can see exactly this happening. So at negative 2, 0, we see the graph crossing through the axis there. And then at the point 3/2, 0, we see that the graph bounces off the axis. Also notice our end behavior. If we look at this, there is a factor of 1 and 2. That is, if we add the multiplicities, we get a 3, which is a degree 3, which is odd. So we know it's going to do opposite things at its ends. The leading coefficient is positive. 0.2 times 1 times 4 is some positive number. And so that tells me it's going to go up to the right and down to the left, which we know. And then one more example, p of x equals x to the 4 minus 4x squared. So to find the zeros, we set x to the 4 minus 4x squared equal to 0. And then we can factor by taking out a common factor of x squared, which leaves x squared minus 4 equals 0. And then this is a difference of 2 squares, so we can get x minus 2 times x plus 2 equals 0. So therefore we get x squared equals 0, x minus 2 is equal to 0, or x plus 2 equals 0. So x squared equals 0 gives us x equals plus or minus 0, which is just 0. then x equals 2, and x equals negative 2. So the multiplicity of 0 is 2 because x squared was a factor. Because x minus 2 and x plus 2 have powers of 1, then those have odd multiplicities or a multiplicity of 1. So at 0, 0, the graph will bounce off, since that is an even multiplicity, so it bounces off at 0, 0. It will cross at 2, 0, and the graph will also cross at negative 2, 0. And I have the graph on the screen that I can show you. This is in standard form. The degree is 4, which is even, so we know it's going to do the same things at its ends. The leading coefficient is 1, which is a positive number. So we know it will go up to the right and then also up to the left. And we see that in this graph. It starts up in the second quadrant, comes down through the ordered pair 2, 0, negative 2, 0, which it crosses the axis there. Goes down to some minimum point, and then it comes back up at 0, 0. But notice it bounces off the axis at 0, 0. Then it goes down, and then it comes back up and crosses at 2, 0, and continues up. So it goes up to the left, up to the right, and then behaves as we just identified at the zeros.